Hello 1040 people. Alright, so we are about to start Chapter 7. Now, before we do, you should have gone through 6162 and done the Math Excel for School on 6162 and taken the Chapter 6 quiz on School City. If you haven't done that, this quiz is due on Friday. You need to make sure, I think you got 45 minutes, so kind of pace yourself. There's 11 questions, and do your best. Alright, now, Chapter 7, this is when we're going to talk about models, and what I have up here is data versus models. Now, we're not talking about this kind of data versus models, though I do think this would be pretty interesting to watch data take on these models. Alright, just a Star Trek joke there. What we're actually going to be talking about is this kind of data versus how can we model that. So what we have right here is, this is something about cholesterol. I just grabbed a graph off of Google, but the point is, here's the data as a histogram. And what we're trying to do is, how can we model what's going on here so that we could make predictions? So here are two lines that they said, well, we might be able to use these, and there's more than one way you can make a model, okay? You guys have done lines of best fit before, and those are where you're making models to help make predictions. Here's just another example about, here's the data, and they're trying out a bunch of different models to see which one is best. Now, to kind of put things in perspective, we're having a lot of talk currently about models predicting how bad is COVID-19 going to be. How can we flatten the curve? And those are all models based off of data and predictions. And so we're going to start with a basic introduction to those today. But as you can see from watching the news, it has some real-life applications. Pretty cool stuff. Alright, so let's go ahead. If you're filling out your notes with me, we're in Chapter 7, Section 1. It's going to be a pretty simple day. And then we're basically going to be introduced to the normal curve, which you saw in 1030. So hopefully you're like, I got this, okay? Now, we already talked about this. A model is an equation, table, or graph used to describe reality, okay? Usually we're given the data, we graph, and we need a line or a model that will tell us what's going on there. Now we're going to look at a specific type. We're going to call it a probability density function, also known as a PDF. I know we work a lot with a different type of PDF. This is a statistics type probability density function. Now, this is an equation used to compute probabilities of continuous random variables. We've talked about continuous before. That's where it could take on any value. It doesn't have to be just integers or set numbers. It can be anything. Like the cow milking. How much milk can the cow give us? Okay, now, when we're talking about a probability density function, basically it's going to model what's going on, and we're going to use that model as a PDF here to predict what the probabilities are. Now, a couple of properties with this, and a lot of these should seem pretty similar. The total area should add up to, any guesses? 1. Just like with probabilities, all the probabilities need to add up to 1. Now, this one's a little bit different. What we're going to be looking here is that the height of the graph must be greater than or equal to 0 for all possible values of the random variable. So that kind of relates to when we talked about probabilities, it needed to be positive. Well, now we're looking at a graph, and we're saying the graph needs to be positive. Okay? Now, another type we're going to see here, we have what is called the uniform probability distribution. We're going to see a lot of different types of probability distributions. I guess I should say there are a lot of different types. And we're mainly going to look at two. We're going to look at a normal probability distribution, but to kind of introduce it, we're looking at a uniform probability distribution. This is where the distribution is a distribution where any two intervals of equal length are equally likely. So it gives you kind of an example here where it says, all right, basically we can take on any value between 0 and 30, this is time, and the probability of those is always going to be 1 out of 30. The area here, notice it's all positive, it adds up to 1. Let's just do an easy example on the next page to help this make sense. So notice here, this is called uniform because the heights are all the same. basically the probability of each of these values is going to be the same. Now in a real world setting, that's not very likely, but it's a good way to introduce what's going on here. So let's go to the next page in your note. Alright, this says the graph to the right is a uniform probability distribution function for the distance that a group of toddlers can throw a ball. So we're taking a bunch of toddlers and we're saying, hey, go throw a ball. And we're saying that they can throw it between 2 to 10 feet. And the probability that they throw it 2 feet, 3 feet, 4 feet, 5 and a half, 6 and a third, whatever, it's all the exact same, which is 1 out of 8. Now we want to find that the probability is between 6 to 9 feet. The best way for us to do this is kind of just mark it out, okay? It won't be exact, but let's try to do that. So I've got 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to label that. Now what we're asking here is what's the probability that the toddler will throw up between 6 to 9 feet. And notice here we're using the it's greater than or equal to 6. That means we're including 6. And it's less than or equal to 9, so we're including 9. So we're saying what's the probability it's going to be in that distance that the toddler throws it. Okay, now to do this, what we're going to do is break this down. Notice the probability is 1/8. And if we were to break this down into a bunch of rectangles, let's count how many rectangles there are. 1, 2, 3, 4, 5, 6, 7, 8. So if all of those need to add up to 1, how much is each rectangle worth? And it's going to be worth 1/8. Alright, now, our question is what's a probability that is between 6 to 9? Well, that would be, let's add up these areas. Between 6 and 7 is 1/8, between 7 and 8 is 1/8, between 8 and 9 is 1/8. So if I just add up 1/8 3 times, I'm going to get that the probability of the toddler throwing it between 6 to 9 feet is 3/8, which is 0.375. Alright, now let's go to part B. Find the probability the toddler throws it at least 8 feet. Now, how do we think of that? At least 8. Do we include 8 in that? Yes, it would be including 8. And what other numbers are between, or would be at least 8? That would be this section from 8 all the way up to 10. So if I add that up, how many rectangles do we have? We have 1/8 between 8 and 9, and then another 8 between 9 and 10, so that's 2/8, which is 1/4, which is 0.25. Alright, now for part C, it's kind of working backwards here. It says there's a 25% probability that X is within blank feet from 2 feet. So if I'm going to start here at 2 feet, how far do I need to go until I've basically come up with 25%, or a fourth of it? Well, as we saw in the last one, 1/4 was 2 of these rectangles, so that means I just need to go out 2 rectangles here, and so that would be 2 feet. So if there's a 25% probability that X is within 2 feet from 2 feet, or in other words, it's between 2 and 4. I just go out 2 feet. So that's an example of a uniform probability distribution. It's uniform because the probabilities were the same for all the different values it could take on. But it's used as an introduction just to kind of show you that, hey, the idea here is you can figure out probabilities by adding up areas under this density curve, is what we call this in AP Stats. It's a probability density function. Okay, so what we're going to do is we're going to change this now. Instead of a uniform probability distribution, we're going to look at a normal distribution. Okay, so you have seen the normal distribution before. In 1030, you saw it, and I think you learned the magic numbers here, and hopefully you have that. But let's just talk about it real quick. The normal distribution of a continuous random variable whose relative frequency distribution has the shape of a normal curve or a bell shape. Now this curve, it peaks at the mean, that's the high point, and what we're going to do is measure how far it goes off base the standard deviation. This symbol here is sigma, that symbol here is sigma. We're going to add the standard deviation, and that gets what's called an inflection point. How I think about the inflection point, that's where the curve is going more down than it's going over before the inflection point, and then afterwards it's going more over than it's going down. So it kind of changes that steepness to where it was going really down fast to now it's going really over fast. So that's what the inflection point is. It just helps you with drawing. Okay, now let's go through and just look at some properties of this normal curve. All right, so first off, it's symmetric about its mean mu. Mu is a population mean. That mean is the same as the median, it's the same as the mode, so it has a single peak, which occurs at the mean when x is mu. The inflection points, we already talked about this, are when it's one standard deviation below or one standard deviation above. That's where it kind of changes that steepness from going more down to going more out. Just like any other probability distribution, the area under this needs to add up to 1. Now, since it's symmetric, if I'm only looking at the area right of the mean, what do you think that's going to be? What about the area to the left? What do you think that would be? And you'd be right if you said it's 50% on the right, 50% on the left, and then it adds up to 1. Okay, now last one. As x gets larger and larger or more negative, so if I'm going to the right or if I'm going to the left, just basically going away from the mean, the graph approaches but never reaches the horizontal axis, which is 0. Okay, so I'm going to put on here horizontal axis, which is 0. We would call that an asymptote if we were in 1050 or if we're in secondary 3. When we're graphing something, it approaches its limit but never reaches. That would be what we're looking at here. All right, let's go here. Okay, now what's awesome about these curves, the reason why we like normal curves is because we can find the area under the curve. Do you remember the 3 magic numbers? If we were here, I would have you chant. What we usually do is we pound on it as we go, boom, 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 and we go 68, 95, 99.7, 68, 95, 99.7, and then we just keep doing that, and I have this whole little rap thing we do. But the point is, you need to remember the 3 numbers, 68, 95, 99.7. If you're like, why on earth do we need to remember those? Well, it's because that tells you how much area is under the curve. The curve, if I go out from the mean 1 standard deviation, so that's going up and I'm going down, then I have a total of 68% of the area under the curve between 1 standard deviation. Now if I split 68 in half, that's how I get 34 above, 34 below. So I could then figure out individual probabilities there. Then I go to 95. So if I go out 2 standard deviations, I go out 95%. Now, how much does that mean each of these get? Well, if we do 95 and we say if we go out 2 standard deviations, we have 95% of our data. Let's take off the 68%, that's 27. What's half of 27 is 13.5. That's how I figure out what goes in each of those. All right, those are 2 numbers, 68, 95. 99.7 is if I go out 3 standard deviations. It's basically 100, right? But it's important that we don't round that. What we're going to do is look at 99.7 minus 95, and that leaves 4.7. If I divide the 4.7 in half, I get 2.35 here, 2.35 there. All right, now that isn't 100%. If I do 100 minus 99.7, I get 0.3, which if I split that in half is 0.15, which goes on the tails. Alright, so hopefully you did that in 1030 where they give you a scenario and you would have to basically take the mean and add on the standard deviation, subtract the standard deviation, and fill in the areas. And then you could say what percent lies within this interval to this interval, and you would be able to answer that, okay? We're going to look at that, but we're going to build off of that as well. Now, just a couple of things here. When we're talking about our normal distribution, how does changing the mean affect it? Well, right here, the mean is 0, and then I change it to 3. And notice it just moved it, it shifted the entire distribution right to the right 3. So, changing the mean obviously changes the mean. Did it change the shape? No, it's still normal. Did it change how spread out it is? In other words, the standard deviation. And no, it didn't change that. It's the exact same shape, still normal, same spread, but it changed where the center is. Now, let's look at this other one. This one was centered at 0 for both. However, for the higher one, the standard deviation is 1, and for the lower one, the standard deviation is 2. What that means is when we look at our numbers 68, 95, 99.7, for this one, 68% is within 1 to negative 1, 95 is within 2 to negative 2, and 99.7 is within 3 to negative 3, because the standard deviation is 1. But now that the standard deviation is doubled, that means I get 68 within 2 to negative 2, 95 within 4 to negative 4, and 99.7 between 6 to negative 6. In other words, the mean did not change on this one, but the spread absolutely did. It was doubled in its width. And notice how, since we had to double the width, the height came down. Or if you think of it backwards, if we start with this wide one, as we start to shrink it in, it's got to be taller to fill in all that area. Now, when we're talking about the shape, what I mean by that is it's still normal, okay? Did it change? Are both of these considered normal curves? And the idea is yes. To be normal, it's single-peaked, it's bell-shaped, and it follows 68, 95, 99.7. These both do. So I'm going to say it's still normal. There are an infinite number of normal curves out there that follow 68, 95, 99.7. They don't have to look the exact same, but they do need to be single-peaked, bell-shaped, and follow 68, 95, 99.7. Okay, so what we're going to do is we're going to look at a few examples here. And as we're doing that, what's going to change is before you've seen this where it asks to give percentages that are exact standard deviations away from the mean. Now we're going to change that a little bit. We're not going to find how to get those, but we're going to just talk about that a little bit, okay? So let's go to this example here. We're talking about refrigerators. Consider the lifespan of a refrigerator that is normally distributed with a mean of 14 and a standard deviation of 2.5. Those are referring to years. So if you buy a fridge, on average, it's going to last you about 14 years. However, the average distance from that mean is going to be 2.5 years. So I'm going to look for where does this kind of change, where's the inflection point? Where does it change from going down to going out? And I'd say it's probably about right there. You don't have to be exact, but that would be one standard deviation above. So now this would be 16.5. And I'm going to keep going out. So I'm going to measure that same distance and say, let's try to do the same thing right here. I don't know why I put 0.25. Just ignore that. That's 16.5. Now we're going to add 2.5 again. That's going to make it 19. And if I go out 2.5 again, that would be 21.5. So what I've done is I took the mean. I added one standard deviation to the mean. I added 2 standard deviations to the mean. And I added 3 standard deviations to the mean. Now let's go the other way. I'm going to look for the inflection point right here. Looks to be right about there. And if I subtract that, I'm now to 11.5. Let's keep copying that about same distance for both of those. So that would now take me down to 9 and down to 6.5. So what I've done here is I started at the mean and now I've subtracted a standard deviation. Subtracted 2 standard deviations. And then subtracted standard deviations. So part A, draw the normal curve and label the horizontal axis. I should give this a label that this is lifespan of fridges. And this is, we want to give the units, this is in years. Okay, so that was part A. Done. Check. What would happen if to the model if the mean were larger? Well, what that's saying is, what if instead of the mean being 14, the mean would be 18? We'd expect the same thing to happen here that we saw in our notes before, where it would just shift to the right. Okay? So I'm going to say it would shift to the right. But it would still be normal. The spread would stay the same. So I'm going to put same spread, still normal. Okay, now let's keep following on here. On C it says, shade the proportion greater than 17 years. So where is 17 at? It's not one of these exact standard deviations. When we've done these before, it says what percent of fridges last between 14 and 19. And we could then use 68, 95, 99.7, fill in those individual percentages, and then figure it out. But notice here, 17 is probably going to be right about here. And that 17 is not one of the standard deviations. It's saying, what is the proportion or percentage greater than this? That would be looking like right here. How do we figure that out? We can't use 68, 95, 99.7 here. Alright, well, it actually tells us here, if you look at part D, it says, suppose the area to the right of 17 is 0.1151. So the area all adds up to 1, or 100%. But the area to the right of 17 is 0.1151. What does that mean? Well, we're going to fill this in here. The probability that a randomly selected refrigerator will last more than 17 years is 0.1151. So you could think of it as just choosing one fridge at random. What's the probability its lifespan is greater than 17 years? It's 0.1151. Or the proportion of refrigerators that last more than 17 years is 0.1151. So if you're thinking of randomly choosing one, or if you're thinking of all possible refrigerators of this style or whatever, either interpretation is correct. And this is going to be more the route that we're heading, is that we're looking at this normal distribution and we're saying, hey, what percent of the fridges last between here and here? And they're not exact standard deviations. I'm not going to teach you how to do that right now, but it's really not that hard. Okay? Right now it's just setting the foundation of, do you understand how we're getting that? So do you understand what the basic concepts are? Setting a foundation. Okay? Let's just do one more example, and then that's actually it for today. Pretty easy. Alright, so Elena conducts an experiment in which she fills up the gas tank of her Toyota 40 times and records the miles per gallon for each fill-up. She determines the mean mile per hour of her car is 24.6 miles per gallon, and the standard deviation is 3.2 miles per gallon. Alright, so what's going on here? We're basically doing miles per gallon, right? We're looking at her gas mileage. Now, I'm looking at this. One thing you have to watch out for is, does it ever say it's specifically normal? And I don't think it does. However, we're going to talk about this as we get later on. Since her sample size was greater than 30, we can basically assume normality. Good things happen when we take larger samples, and as long as our sample size is greater than 30, we're going to assume it. So if you're wondering, like, why are you doing a normal curve? We'll talk about it more later, okay? All right, so what we're going to do is let's just start at the mean, right there at the middle. All right, her mean miles per gallon, I think that was supposed to be a G, is 24.6. And then we're going to go up by 3.2. So I look at where does the inflection point, it looks right about there. And if I add 3.2, that's 27.8. And then let's go up again. This will be 31. Go up again. This is 34.2. Now we're just going to subtract